The purpose of this report is to explore the effects of insulation on food containers and determine the overall heat transfer coefficients for the containers. One day, after getting food poisoning from poorly stored fish, I wondered if there is a better way to store and transport food for lunch. Up to this point, I had been using simple plastic Tupperware containers to store the food, but nothing to insulate the containers. A thermos vacuum-insulated food jar with a removable plastic container claims to keep things hot for up to 4 hours or cold for up to 6 hours. Compared to similar products on the market, this seemed to be pretty good. This report was intended to test those claims by determining the overall heat transfer into the removable plastic container with and without the vacuum-insulated thermos shell. The overall heat transfer coefficients of the container could be calculated from the experimental data using the energy balance equation and the latent heat of fusion of water. The heat transfer of a system can be determined using the energy balance equation. In this experiment, energy is entering the system while no energy is leaving and no energy is being generated. Consequently, the energy coming in is being stored by the system. The energy stored by the system during phase change is the mass flow rate times the latent heat of evaporation, or, for this experiment, the latent heat of fusion. This can be determined experimentally by measuring the mass of water that undergoes a phase change in steady state over a specified period of time. When the amount of energy stored by the system is determined, the amount of energy entering the system is also known. The amount of energy entering the system is equal to the overall heat transfer coefficient times the area times the difference in temperature. The heat transfer into the system, along with the change in temperature, is measured. This allows for the overall heat transfer coefficient to be calculated. The overall heat transfer coefficient becomes the mass flow rate times latent heat of fusion of water over the area times the difference in temperatures. For the purposes of this experiment, the heat transfer through the cylinder can be considered one-dimensional if the temperature gradient is only in the radial direction of the container. The heat transfer coefficient was determined by observing the phase change of ice blocks inside each of the container configurations. To produce the desired experimental data, blocks of ice were frozen inside the thermos container as well as the removable plastic container. The blocks of ice were tested inside the thermos container, the removable plastic container, as well as both the containers while together. Data was collected from multiple tests using all container configurations: the clear plastic liner and the stainless steel shell by themselves, and the liner inside of the outer shell. A thermocouple was attached to the outside surface of the thermos and plastic insert during the experimental procedure of the given configuration. A thermocouple was also attached to the outside surface of the plastic liner in addition to the outside surface of the thermos while the two containers were being tested together. The ambient air temperature was also recorded. The ice block temperature was recorded to assure thermocouple accuracy and was found to be within 1/10 of a degree. During the experiment, it was assumed that the temperature of the container was steady state and that the inside of the cylinder was in complete contact with the ice water. The containers were left in each experimental configuration for several minutes and quickly drained before any measurements were taken. After reaching a steady state, each ice block was allowed to melt in its given configuration for a predetermined amount of time. After the time was reached, the water that had melted was carefully poured in another container and weighed. Careful handling of the ice block and containers was used as to not disrupt the steady state temperature. In addition to the already well insulated top and bottom of the thermos container, styrofoam blocks were used to better insulate the top and bottom of each container configuration during the experiment in order to ensure the temperature gradient was in the radial direction of the cylinders. The addition of the vacuum-insulated metal shell to the plastic container increased the heat transfer performance by a factor of 24 compared to that of the plastic container alone. The overall heat transfer coefficient for the plastic container was 48.5 watts per meter Kelvin. In contrast, the overall heat transfer coefficient for the thermos container was only 3.4 watts per meter Kelvin. The containers together brought the coefficient down to only 2.0 watts per meter Kelvin. This indicates that overall performance of the thermos container was 14 times that of the plastic container. Combining the containers gives a performance 24 times greater than that of the plastic container alone, and the performance of the combined containers was only 1.7 times more effective than that of the metal container alone. It is recommended to store any refrigerated food in a vacuum thermos container as opposed to a typical plastic container, as it will keep the contents cold for roughly 24 times as long. Keeping food out of the optimal growth range for common bacteria ensures that food stays good longer. As can be seen in the chart on the left, the growth rate of many bacteria types increases greatly at any temperature above 0 degrees Celsius. This experiment helped to validate the importance of keeping refrigerated foods in a well-insulated container when left in room temperature for an extended period of time. Doing so will help eliminate the chance of getting food poisoning.